The security of the electromagnetic spectrum has reached tremendous importance to society. Wireless communication technologies such as 5G cellular networks, communication with aircrafts, and global navigation satellites must be protected. A game changer to cope with this problem is to leverage a network of flexible spectrum sensors coupled with big data analytics. Following this vision, the SOCRATES project started in June 2018 with the objective of delivering a collaborative security system to protect our electromagnetic environments and the users and the services that depend upon it. Adopting an agile approach, SOCRATES is building, demonstrating and showcasing early prototypes throughout the project.
Wireless communication technologies in use today use the frequency range between several kHz and up to 6 GHz. In this range, we already find many applications like FM and AM radios, airplane communications, Wi-Fi technologies, but also the recently deployed 5G technology. Now, to capture this very wide frequency range, we need specific hardware like the electrosense converter board that can take all the frequencies in this range and convert them to an intermediate frequency that can be captured by a very low-cost software-defined radios. Other than that, we need multiple antennas which can be tuned at the different frequencies and that can capture the full range.
The typical software-defined spectrum sensor in crowdsourcing deployments consists of a radio frequency receiver like this one that you can see here for signal acquisition and a Raspberry Pi for signal processing. The sensors scan the electromagnetic spectrum in a coordinated manner and send spectrum data already processed to the backend. Our software can run in different modes, PSD, IQ or decoding mode, depending if we want to send power spectrum measurements, IQ data, or information already decoded by the spectrum sensor.
The new ElectroSense architecture allows users to decode specific parts of the radio spectrum. This enables the possibility for users to know what's going on in the spectrum in different parts of the world.
Via a friendly web interface, any user will be able to select any sensor and decode various signals of Earth, such as FM, AM radio, ADSB, AIS, LTE, and ACARS.
Low-cost spectrum receivers have strong limitations in terms of sampling rate, making it impossible to decode wideband signals. We envision a scenario where non-coherent receivers are distributedly deployed in area of interest by multiple users. They scan the electromagnetic spectrum collaboratively to cover a larger bandwidth than one single receiver does. We have developed algorithms to aggregate and fuse this electromagnetic spectrum and then enable the collaborative signal reconstruction and decoding in the backend.
We are working on novel methodologies that can work with very low-cost receivers such as RTL SDR to localize the wireless transmitter. When multiple spectrum sensors receive a signal, you can not only do collaborative decoding of a wideband signal, but also localize transmitter. Transmitter localization can have a key role in spectrum monitoring activities, as once the anomaly in the spectrum has been found, the capability of detecting its position can allow the actuators to react fast.
Decoding requires the information about the modulation use. My colleagues assume that that information is ready to work on their research problem. I work on detecting modulation blindly. Our automatic modulation classification framework uses the data available in the ElectroSense network and trains a modulation classifier using deep learning. Traditional deep learning schemes that are good for image processing can be applied to waterfall plots of power spectrum, but they need to be adapted to work efficiently with specific radio signals. The symbols we need to detect here are radio symbols and not cars or pedestrians for image processing. What's also challenging for our problem is that fact that our data has a lot of noise and also the signal quality coming from low-cost spectrum sensor is not that always good.
Beyond modulation classification, we are also interested in the general problem of detecting anomalies in the wireless spectrum. Wireless spectrum anomalies are very challenging to detect because of the sheer complexity of the wireless spectrum use. Wireless spectrum anomalies can take a large amount of forms. It can be an unwanted signal in the licensed band, or it can be a missing signal, like a missing base station at a particular location. This makes labeling of these anomalies very tedious and difficult. We have developed both unsupervised and semi-supervised methods to detect these anomalies, leveraging the recent advancements in deep learning and using ElectroSense data. With these developed techniques, we can accurately detect, classify, localize, and even present these anomalies to users with minimal user interaction.